Norton equivalent circuit and maximum power transfer. The Norton equivalent circuit and the Thevenin equivalent circuit represent the same information. And so once you have one, it's very easy using source transformation to find the other. Deriving R Norton, you follow the same process as you would to find R Thevenin. Instead of finding the Thevenin voltage, which is the open circuit voltage with no load attached, you find this short circuit current with no load attached. One can find the Thevenin equivalent and use source transformation to find the Norton equivalent. One can find the Norton equivalent and use the source transformation to find the Thevenin equivalent. Let's talk a little bit about the source transformation. Now, we have seen before where we can have a voltage source here and a resistance here. And if we put the resistance now in parallel with the current source and transform the current source into V divided by R, we can transform this circuit into that. And we can go backwards and forwards. And so, if it's easier for you to find the Thevenin equivalent, but you really needed the Norton, I suggest find the Thevenin, use source transformation to get the Norton equivalent. Now, this leads into maximum power transfer, which is easy to see with a Thevenin equivalent or even a Norton equivalent circuit. So when we're talking about maximum power, a Thevenin is really just a voltage divider. So if this is a Thevenin equivalent circuit and I put an RL between A and B, it's just a voltage divider. R with the voltage proportional to this value of R to that portion of RL. And we'll find out that the maximum power transfers when RL equals R Thevenin. Just like in the Norton case, this happens to be a current divider, and the voltage is the same across the parallel resistors. And the maximum transfer occurs when RL equals Rn. Now, this is derived pretty well in the book, I have to say. So I'm not going to repeat it here, but I wanted to show you how to use LTspice to automatically change parameters so that we can experimentally, in quotes, verify that this is true. So over here I have a Thevenin equivalent circuit. Right here is .opt, which means run a DC simulation. This is called R Thevenin, and the value is R Thevenin in brackets. And what that means is it's a variable. And so if I go down here into these commands here, notice dot parameter R Thevenin equals 10K. That means that'll be fixed. All right. Now over here I have R Norton, but it's the same value RTH as the 10 kilo ohms that I put here. This V, it's a variable again, V1, and I just set that equal to 10 volts. And over here I have in, or it's the I Norton. And here I've programmed it. I Norton equals 1.0 times V1 divided by R Thevenin. That's the source transformation. Then I step parameter R2 from 1K to 50K in steps of 1K. And so see R2 here, that value, this is the name RL Thevenin, here's the name RL Norton, but they have the same value of R2. And what this will do is run DC simulation at this R2 equaling 1 kilo ohm, 2 kilo ohms, 3, all the way on up to 50. If you want to use this file, you can cut and paste this link into the open file pop-up of LTspice, and it'll come right up, and you can see the same results. So let's run the simulation, and you can see that VA equals VN, and just to refresh, that was my node A and that's my node N, and you can see that it's the same voltage. Here it's not shown, but it's the RL value changing from 1K all the way up to 50. Well, let's look at the power. Now, up here in the title, I had VN before, and I just click on that title and I can type in the current times RL Norton. And over here I can type VA times RL Thevenin, because LTspice will give me these currents automatically. I don't have to calculate it and then substitute it. It's right in there. So V times I equals power, and you can see that they peak in the same place. But it might be a little bit hard to tell that it's peaking right at 10 kiloohms, so I put it in a logarithmic scale, and you can see that the power is the same, and it's happening, the maximum power is happening exactly at 10 kiloohms. Again, go through the derivation in the book, because it's a great review on finding the maximum or the minimum of an equation using your calculus. But this is a powerful technique because you can change variables quite quickly right down here in the parameter statements, rather than have to change a value, run it over, change a value, run it over. And we can see that, yes, these two circuits are equivalent.